And now, ladies and gentlemen, we're moving to a different field. And I'm very, very honored to have Professor Paolo Dario with us. He's the Professor of Biomedical Robotics at the Scuola Superiore Sant'Anna in Pisa. And those, of course, you all know the Leaning Tower of Pisa and the alleged story that Galileo proved that heavy and light weights would fall at the same speed and that gravity is constant by throwing rocks of different weights from the Tower of Pisa. So it is said. It's a great center of learning, and of course we have great professors with us. But he's also a visiting professor at Waseda University in Japan and Zhejiang University in China, and he's the coordinator of the CRIM, Center for the Research in Microengineering Laboratory of the Scuola Superiore Sant'Anna. He serves as director of the Polo Sant'Anna Valtera and the Scuola Superiore Sant'Anna, and since September 2009, he has been the coordinator of the newly established Center of Micro-Robotics at the Scuola and the Italian Institute of Technology. Now, the main research interests are in the field of medical robotics, biorobotics, mechanotronics, and micro-nano engineering. And he's been the president of the IEEE Robotics and Automation Society in the years 2002-2003, and he's received so many awards, including the Berger Award, but I'm not going to cite them all because I want to give him time to speak for himself. But I will tell you this, Professor Dario has really been a pioneer in studying how we can mimic motions of animals in nature in order to solve problems, medical problems for humans. It is a field that combines imagination and enormous knowledge. So please join me in welcoming great pioneer, Professor Paolo Dario.
Thank you very much. Of course, it's a real privilege, an honor, a pleasure to be here. This is my first time, and I'm really impressed. Living in history and having the privilege to talking to so many young and passionate people and students about robotics, in particular about biorobotics. This morning there was some, let's say, point that was raised about the issue of biomimicry, and I think I'm going to present some ideas and some real practical implementations about this field that is at the border between biology and artificial machines, like now, and that also combines science and technology. So, first of all, what is biorobotics and why we can define and we can say and talk about biorobotics, science and engineering. First of all, we are addressing biological systems. And in order to do that, traditionally, biomedical engineers, for example, have used engineering analysis and modeling methods with the goal of developing artificial systems, for example, surgical robots or rehabilitation robots, to improve the performance of biological systems. So understanding biological systems in order to develop better machines. But there is another use of engineering analysis and modeling of biological systems, and this is the development of physical models. Actually, physical models are robots. Now is a physical model of a human, and this direction leads to the development of bio-inspired robots that can have their useful applications, can become products, or we can develop biomimetic robots that in a way do not have a specific engineering application, but rather they are instruments to validate the engineering analysis and modeling. So they are scientific instruments. So In Biorobotics, we have science because we are using robots to discover new principles, and we have engineering because we are using robots to invent new solutions to a wide range of problems. In particular, if we consider the traditional approach, scientific approach to problems, let's say the problem of manipulation, we know that we formulate some hypotheses and models, and when we do that in the neuroscience, what we do is we develop human models, we develop word model, and we develop model of the interaction between the human model and the word model. Doing that, we introduce some approximations, so this is why sometimes in the past the neuroscientists used, and still now, animal models as a substitute of human model to understand the relation between a living being and the world. Well, it is our expectation that we can do this, that we can substitute this substitute of human with a robot, a machine, an intelligent machine with high performance. Actually, you know that this approach was proposed years ago by a few scientists, including Rodney Brooks, that virtually introduced a paradigm shift in artificial intelligence, claiming that the only way to understand the brain is building a body. And this happens in the 80s, and this was the end of the traditional approach of pure logics to understand intelligence. Rather, the approach, of course, this is not died, this approach, but the new approach is more and more understanding brains by building bodies. So this is really the role of biorobotics science. It is building a body to understand the hypothesis and model and to make experiments using these robots so that the model can be validated. So this is the idea about biorobotic science. And this can be done not only in the field of humanoid, but can be done by investigating virtually any species of biological systems. For example, even a worm, making a hypothesis and model, building a robot, a biomimetic robot, making experiments and eventually validating the model. Incidentally, the fact that this approach is now recognized as a scientific approach is demonstrated by the fact that an increasing number of papers using robots exactly in this way are published on Nature and Science, essentially demonstrating that this is a sound approach. Now, said about the method, let's go to the implementation. First of all, the humanoids. We have been working on humanoids. This is our humanoid robot that we developed 15 years ago, actually, and in which, for the first time, well, in our lab at least, we worked with the neuroscientists to understand, using the robot, how grasping and manipulation is learned in children. And we are now pursuing more and more this approach. We started, as I said, with this taking into account as a problem, and the scientific problem was to understand how sensory motor grasp control develops. And according to Piaget, a well-known psychologist, there are 5 steps in children that demonstrate this. And this is what we have done, actually. I'm just showing a few examples of results that we achieved years ago. You see, the robot is used. These were quite primitive at that time were, of course, very advanced experiments in which we let the robot understand and learn manipulation by using vision, attention, and a multi-finger hand for grasping. There are continuously new problems or new hints that come from neuroscience and that can be included in robotics. For example, the case of anticipation. You know, most robots in general work trying to walk, observing the ground and trying to keep the equilibrium, the balance, while humans and animals do not do that. All animals would die if they would behave in a closed loop approach. Actually, closed loop is not what works in nature. In nature, it's forward. Actually, the idea is to anticipate the problems, trying to catch the prey, try to escape, and then, you know, you can survive if you're faster. So, anticipation is very important. It's very important in locomotion, it's very important in manipulation, gaze fixation is very important. You know, we just started a new project, a European project in this, and together with neuroscientists like the group of Professor Alain Berthoz, who is the person who essentially conceived this idea of anticipation. So we are going to use this platform, and we are trying to improve dramatically the performance of this platform by using this kind of neuroscientific model. So this project is just started, so we don't have at this time extensive example to show, except the fact that we are implementing these models in some subsystems like manipulation. So this time, what we expect to do is to introduce a sort of discontinuity in the behavior of robots, of humanoid robots, using inputs, using knowledge from science, so essentially predictive behavior, the very important role of the vestibular system. You know, most robots in the past did not have any vestibular system, while the vestibular system is a key in all animals, in all living systems, is our reference platform for all behavior. But since it is hidden inside our head, it was as a sort of lost sense. But of course, the neuroscientists know that very well. You know, there are many examples of fusing, of combining neuroscience and robotics, leading to, based on this approach, to many different areas of research. For example, the one on the hand. We know that the hand is important for reaching, for grasping, for manipulation. It's also important for exploration, it's important for gesture. The dream of many researchers has been to develop prosthetic hands that could be connected to the human body so that they can be felt by the brain as a natural part of the body and could be controlled directly by the user brain by means of real-time decoding of reference signals. Well, we have been working for years on that. This was a first example. Actually, it was my dream 20 years ago, and we went through a number of steps whose critical part was the interface between the nervous system and the hand. Actually, in the next session, there will be colleagues talking about that extensively. But another very important issue are the hands. And we have been developing hands for many years. Hands have many degrees of freedom. You see here, this is a hand with 16 degrees of freedom, total actually 6 degree of mechanical motion, real ones, so an under actuation. And recent results have led to progressive miniaturization. You see on the left the one intermediate hand, on the right a smaller hand, so that this hand has been actually tested. You see, those are experiments that were carrying on in an amputee person. This is a myoelectric control, so the person controlling the hand by means of myoelectric signals. But more recently, we have been able to implant semi-permanently. I think Professor Warwick will also present results on that. But this implant of electrodes has been made so that first in Lund in Sweden and then in Rome, a real patient has been able to control the movement of the hand by is taught. There are papers describing this. Also, very important is the field of neuro rehabilitation. You know, robots have been used for about 20 years, actually 30 years, as tools to help scientists, the neuroscientists, to understand how the motor cortex codes the kinematic and dynamic upper limb movements. But at the same time, these kind of tools, these robots have been and are now being increasingly used for rehabilitation purposes. You see here, those are results that we have obtained with real patients, actually a huge number, 108 at that time, now more than 130 patients with stroke being rehabilitated with very, very promising, very interesting results by robots. So, robotic therapies. Animals can also be modeled for bioinspiration. And in our laboratory, we have created a sort of zoo in which we have many different animal species and even plants that we use as models to investigate scientific problems, but then also to find engineering application. You see again the mix of science and technology, science and engineering. For example, the worm. The worm is a very, I would say, human animal, but it can be investigated using engineering principles. So, for example, modeling the mechanics of locomotion, and actually as also developing, as you see, the counterpart. You see, and using the counterpart to validate models, also to understand, as we did here, the role of seta. You know, seta are sort of small, very, very small legs that the animal, the worm, is using. You can see these small black pins. And, by the way, you see that we published this paper on the philosophical transaction, the Royal Society of Mathematics, Physics, and Engineering, so it's a purely scientific journal. But then we built artificial setae, and we used this setae to understand, to investigate the role of friction in locomotion. And so, taking hints from nature in order to understand, for example, like in this case, the role of friction, the anchoring model, the Coulomb model, so different scientific issues, and developing different technological solutions. Now, these technological solutions have been used to develop a very, very practical solution to a very important clinical problem, you know, the problem of colonoscopy. All of us know that colonoscopy is very important, especially after 50s, as an examination for detecting colon cancer early. And here the idea, and not only the idea, is to take inspiration from the inchworm movement of the worm in order to develop a painless colonoscopy system. And this painless colonoscopy has already been developed and tested now in more than 400 human patients. So, once again, the link between science and engineering. Well, beyond the worm, well, going from the worm for colonoscopy to a capsule for the endoscopy of the entire gastrointestinal tract. So the idea is swallowing a pill and using the legs to move. So we developed a model for free body kinematics, then we developed a number of solutions, including multi-legged solution. You see here if I am able to show, yes. Here, this is the approach that, the engineering approach of leg locomotion. But recently, we moved from leg locomotion to magnetic locomotion. Actually, we are using leg locomotion too. You see here is an animal experiment in which you see the capsule inside the colon levitating by means of a permanent magnet that is moved by the robot. So essentially, the idea is to have this capsule moving inside the body of a person by means of the external, the control of the robot. You can imagine how the robot can be fine in control. In fact, we have now a number of applications that are coming, including clinical ones from a new generation of capsule like this. And then you can think like for swarms in animals. Well, why should I have just one capsule? Maybe I can have more capsules. And this is the basic idea that led us to the development of the new kind of surgical procedures in which a person is swallowing many different pills. These pills can be assembled so that a new tool is built in the body of the person. You see here how a complex surgical tool can be built and disassembled inside the body of a person. And here we have the overall architecture that we are developing within the framework of a European project. You see, this is the modular approach. It's a totally non-invasive because the surgery is performed either through the mouth or through the umbilicals, leaving no scars. And actually we have now a new project in which we are exploring this frontier in the area of blood circulation, so in the millimeter scale. There are other hints that come from nature, for example, from jumping. You know, jumping is a very interesting technique for locomotion that is particularly effective in some circumstances, for example, in the negotiation or uneven terrains. And in order to explore this, so you see, better understanding from an engineering point of view the biological mechanism of jumping, but also taking lessons from this in order to develop jumping mini robots. And the potential outcomes are many in different fields. So we have analyzed different jumping insects. There is, we talk about biological diversity, huge variety. We selected two because they're easier, have a very interesting jumping performance, and we have raised this. By the way, it is quite interesting maybe to observe that we are doing this in an engineering laboratory, just to show the interdisciplinarity and the transdisciplinarity of this research. And the same can be done with mosquito. The jumping of mosquito is extraordinary from an engineering point of view. So those are very, very effective mechanical solutions that we are very much interested in imitating. So we have started by performing numerical analysis of this behavior. Essentially, what we learned is that the mechanical structure, there is not much intelligence in these animals, but there is a mechanical intelligence. It's what is now called embodied intelligence. It's an intelligence that is the result of mechanical solutions, so the bones or the legs and the muscles, the sensors, and of course the brain, especially the peripheral, the neurons and so on. And of course we have developed a jumping robot. I don't have time to show everything, but actually we have written very nice papers because we discovered something that was not known before. That is, for example, the fact that acceleration is constant during the jumping phase, that biologists have not observed. So we have observed together with biologists this new knowledge. And then the lamprey fish. The lamprey is a prototype, is a vertebrate prototype, has a very important position in evolution. And it developed all the basic features of the vertebrate nervous system. You see there the lamprey 530 million years ago, and then the salamander also. And what is very important is that both possess at a very nice level, without legs and with legs, without legs the lamprey, with legs the salamander, the same spinal locomotion system of the central pattern generator that we find in cats and humans. So they are very, very important say research to perform. And you see here, this is our team is a mixed team of neuroscientists and roboticists. We work together, and we are working, in order to investigate, in this case, the transition from aquatic to terrestrial locomotion. You see, this is a paper published on Science describing exactly this, how the robot, together of course with the real animal, can be used to elucidate this kind of issue. You see here again the role of embodied intelligence, the preflex, and how different technologies can be adopted to fabricate these artifacts. You see here, by the way, this is a patented technology. We sold the patents to two big companies. It's a new kind of very high efficient magnetic motor that we have developed to actuate this. Sorry, I hope that this video works. Yeah, more or less. Okay, yes. So you see, this is a quite complex behavior of the salamander that then is also swimming. You see, wireless, by the way, and those are again preliminary experiment, but with a very, very sophisticated scientific model behind it and technological solutions. Then the octopus, I'm almost going to the end. The octopus is an extraordinary animal, by the way. It's very good also to eat, incidentally. In Italy we like it. In the US I know you don't, but this is a big project that is aimed at investigating the octopus as a paradigm of embodied intelligence. You see, the idea is adaptive behavior is not just control and computation, but is really the emergence of this complex and dynamic interaction between the morphology of the body, sensory motor control, and environment. And you see, this is the basic idea. The nature of the human mind is largely determined by the form of the human body. See, so this combination of mind and body is something that is now widely accepted. So, first of all, understanding and analyzing the behavior of the octopus. I just have a few videos here, but again, it's quite impressive. Our octopus open jars very, very quickly to get food inside. So, it's a paradigm of intelligence, but at the same time it's a paradigm of soft-bodied robots. Can you imagine a robot that, like this octopus, can pass through a very, very tiny pipe, moving across vents and so on? You can imagine, it's clearly a fantastic example for engineers. And so it has no rigid structure, virtually infinite number of degrees of freedom, can bend in all directions. It has a tremendous elongation of each arm. It's a variable and controllable stiffness, a very strong force actually, and many other features, manipulation capability, distributed control. So a very, very interesting paradigm for new science and new technology. And so we are ready after 1 year of the project. We are investigating the anatomy of the octopus arm with the longitudinal muscle, transversal muscle, the oblique muscle, and building analogs. Those are preliminary work of soft actuator, and those are just a few preliminary examples of how we pursue this goal. So, in conclusion, it is clear that Biorobotics is really a fascinating challenge for interdisciplinary research. It's important to combine neuroscience model and robots, but it is very important to do more. That is really to incorporate neuroscience model into new generation of jointly designed robots, so that after validation, because this is the idea, better technology can be developed, leading to many new applications, and at the same time also new science can be obtained. Incidentally, for engineering students, this is very important. Actually, in engineering, in robotics, we all know that the impact factor of engineering journals is like 2, maybe, or less. The impact factor of biological journals is 2, 3 times, 10 times, and so on. So it's also very, very useful for academic career, this kind of collaboration. This was mentioned this morning. I repeat this for students. So working in this field is really very, very interesting. So the real conclusions are that science-based robotics has the potential to generate disruptive and non-incremental innovation. That's a very important lesson. In general, this is the secret. I'm saying this here in Alexandria, in the Bibliotheca, where knowledge was stored first by humankind. All different kinds of knowledge. Working just in a small area is stupid and is no longer really effective. I think of course it's important. I'm exaggerating, I'm provocative, of course. But it's very important to bridge different cultures, to make progresses that otherwise would be very difficult. So this is a secret, it's always been important, it's more important now than in the past. The extreme variety of behaviors and function solutions that can be found in the biological domain are an endless source of inspiration for engineers. It's tremendous amount of engineering solutions that can be found in nature. And at the same time, robotics is a very effective tool for biologists to address problems in a different way. So use robots as tools for investigation. It's very, very important, and it works. Biorobotics is attractive. You are seeing now, and you can imagine how many students we have. Actually, my team is about 140 people, having a lot of fun, I can assure you, working and playing with fish, birds, crickets, and of course, real robots, and can bring to many industrial applications. So, thank you very much for your attention.